Hello, this is Nicholas. I'm going to be doing an extension of the linear differential equations I did in the last video, and this extension is known as Bernoulli equations. So the idea was that in the last video, we just had the linear differential equations, and those were in the form dy over dx plus p of x y is equal to q of x times y to the n. Oh, I'm sorry, spoiler. Just times no y, just the q of x. Bernoulli equations, we say, all right, we take that, and you probably guessed by now, and we multiply this q of x by a y to the n, where n is any real number. And we want to try to force this form into this form because we have an integrating factor for the linear differential equation. And if we could force the Bernoulli equation to a linear differential equation, then we would easily be able to solve it. So let's, there's YouTube and things. Let's take a look at this general form. So we multiplied by that y to the n right here at this q of x. Now, I don't really like the y to the n there because when I go to integrate, I'm going to be integrating somewhere. When I want to integrate, I just want one of my sides to be a polynomial in terms of only x or only y so that I can easily find an antiderivative. So I'm going to get rid of that y to the n by multiplying by a y to the negative n on the whole equation. So y to the negative n times dy over dx plus p of x y to the 1 minus n is just q of x. Now this looks a little similar. It roughly fits the form of the power rule because when I differentiate this 1 minus n here, or in other words, negative n plus 1, then the power becomes a negative n. So the idea is I'm missing, if I were to differentiate this y to the 1 minus n, I'm missing a factor of 1 minus n here. So let's multiply by that and see where that takes us. So I'm going to multiply the whole thing by 1 minus n. So we have 1 minus n y to the negative n dy dx plus p of x y to the 1 minus n times 1 minus n is q of x times 1 minus n. And this n and the x, I know before I said that I want one of my sides to just be solely in terms of x. It doesn't matter that this 1 minus n is here because it's a constant anyways. Whatever it is, it's a constant, and so that's not going to mess with the integration at all when we get to that step. Now, if you notice that this side here is the derivative of y to the 1 minus n with respect to x, that's exactly why I multiplied by the 1 minus n there. So plus p of x y to the 1 minus n times 1 minus n is q of x times 1 minus n. Now I'm differentiating this y to the 1 minus n. I would rather not differentiate that. I would rather just differentiate a function without that power of the 1 minus n. So I'm going to do a change of variables. I'm going to let y to the 1 minus n be equal to u. Now I have the derivative of u with respect to x plus p of x u times 1 minus n is equal to q of x times 1 minus n. And this might look like we have more than two variables, but again, the n is just a constant, so we really only have two variables here, an independent u and a dependent x. And now this differential equation, also it might not look like it, but it is in this linear form here that we discussed before, again, the only difference is that we're just multiplying by constants here, but that, again, does not mess with the integration when we multiply by the integrating factor. So this function here is guaranteed to have a solution. It's in the form of a linear differential equation now, and it has a solution by the integrating factor. So, let's try an example. Well, let's try. Oh, I don't know. Let's try dy plus 1 over x y dx is equal to 3x squared y squared dx. I notice right away that I can, if I multiply, it looks like I've divided out by a factor of x on the left side, and if I were to multiply by an x, it would fit the product rule, so I'm going to do that. So I have x dy plus y dx, that's exactly what I want, is 3x cubed y squared dx. This is the derivative of xy with respect to x. And it was originally a dx here. So that's 3x x cubed y squared dx. I can integrate both sides with respect to x. I already have that. Well, I already have a dx on the right side. So that means that xy is 3/4 x cubed. 3/4 x to the 4th y squared, since y is a constant with respect to x, plus c. And that's a solution to that differential equation. Maybe a little more complicated of an example. If I have dy over dx plus 1 over, say, x minus 2y is 5 times x minus 2 square root y. So, if you remember in the general derivation, all I did to go from the original Bernoulli equation form to a form that fits a linear differential equation is I multiplied by a y to the negative n times a 1 minus n. And so that's exactly what I'm going to do here. Here, n is equal to 1/2 because this is really our y to the n term, the square root y, and then square root y is y to the 1/2, so n is 1/2. So I'm going to multiply the whole thing by y to the negative 1/2 times 1 minus 1/2, or just 1/2. And that's where I'm getting what I'm multiplying by is from the general form. So 1/2 y to the negative 1/2 is what I'm going to multiply by. So 1/2 y to the negative 1/2 dy dx plus, I'll write it like this, 1/2 over x minus 2, and then y to the negative 1/2 times y, that's y to the 1/2, is, that's 5/2 x minus 2, yeah, because y to the negative 1/2 times y to the 1/2 is just 1. So this here is the derivative of y to the 1/2 with respect to x. And I'll just keep it the same. Plus 1/2 times 1 over x minus 2 y to the 1/2. And that's 5/2 times x minus 2. Now, I'm going to, just like how I did in the general derivation, I'm going to do this substitution next. So I'm going to let, just what's inside here basically, I'm going to let u be equal to y to the 1/2. And if you notice, if you multiply by the y to the negative n times 1 minus n, you might have noticed in the general derivation and in here, and that's what makes this substitution so powerful, is that every time you multiply that, this second term here on the left side is always going to end up being what you substitute in for y. That's why we multiply it by the y to the negative n times 1 minus n so that it can fit the product rule. Again, that's the whole idea here. So du over dx plus 1/2 times 1 over x minus 2 u. I'll just write it as u over x minus 2 is 5/2 x minus 2. And now we can get the integrating factor for this because it's in the form of a linear differential equation. So now that it's in the linear differential equation form, notice that this term here is really 1 over x minus 2 times u. So this 1 over x minus 2, that's p of x in our linear differential equation form. So our integrating factor mu of x is e to the integral of 1 over x minus 2, or in other words, natural log of, and you don't really need parentheses because we're we're assuming domain restrictions to begin with. So I'll just do parentheses x minus 2, and that's just x minus 2. So I can multiply the whole thing by x minus 2. X minus 2 du over dx plus 1/2 u. It's nice that the x minus 2 cancels there. It's 5/2 times x minus 2 squared. And this is x minus 2 times the derivative of u. So this is, in other words, the derivative of x minus 2 times u with respect to x. And this is 5/2 x minus 2 squared. Can integrate both sides with respect to x. So x minus 2 u is, okay, we divide 5/2 by 3, that's 5/6. So 5/6 x minus 3, or x minus 2 cubed, that's why I wrote the 3, plus c. And we're not quite done yet because u is y to the 1/2. So the general solution is x minus 2 square root y is, actually I'll write it like this, 6 times x minus 2 root y is 5x minus 2 cubed plus just some different constant, I'll call it c1. And that's the general solution to the Bernoulli equation. I hope that made sense and you understood me well.